In this section, we'll talk about expectation and expected values. And so expectation and expected values are kind of the same thing, but we'll look at those in a little bit more detail. And we'll start out with a formula. So we can define an expected value or an expectation of the mean of a random variable x, which has a given PMF of the PMF of x, by using this formula here. And this formula basically says that the expected value of x is equal to the sum over every possible value of that random variable x, that is little x. And that sum is going to be of the value of little x, whatever outcome that may be, multiplied by the probability mass function of that little x, so the frequency of that little x. And so the expected value really is just the frequency of that given value of the random variable multiplied by the value of the random variable. So to look at this in more detail, let's just jump into an example. So let's assume that you're playing a game of some form 1,000 times, and that each time you play that game, you gain a certain percentage or a certain amount of money, a certain gain factor, if you will. So if the game has the following gains, then what can you expect to win at the end of the 1,000 plays? And this is really just an example of expectation. So let's look at a piecewise function here where we have a random variable x that is equal to 1/2 2 out of 10 times, so 20% of the time. And it is equal to 1 5 out of 10, or 50% of the time. And it's equal to 2 3/10, or 30% of the time. So again, we're just saying there's a random variable x, and it has a certain frequency. That would be this column, the probability mass of that given value, for each of the expected values, the actual number that we'll get as an output. And so if we look at this in more detail, then we can really go through and calculate what the expected value of this specific function is. So to do that, all we need is this formula, which is summing over all possible expected values. So what we can say is that the probability mass function for a given x, random variable x, at the value of 0.5 is equal to 2 out of 10, right? That's just rephrasing this over here to put it back in the notation that we've seen earlier. But to find the expected value of x, so again, that's going to be the expected value of the random variable x, we would need to take the frequency, this 2/10, and multiply it by the value, this 0.5, for every value pair, if you will, within this piecewise function, within this random variable x. So in this case, it's going to be equal to 1/2, and we'll just say that's 0.5, multiplied by 2/10, plus 1 multiplied by 5/10, plus 2 multiplied by 3/10. So when we add all that together, we find that this is equal to 12/10, or 1.2. So what we've learned is that the expected value after those 1,000 times is just equal to 1.2. That assuming that everything is normalized, that we've played a sufficient number of times, that we'll end up with a gain of 1.2 based on the possible outputs and the frequency or the probability of each of those outputs. Now, there's some expectation properties that we need to be familiar with, and a lot of these should be really self-evident, so we won't spend a ton of time here. But the first one is that if the random variable x is greater than or equal to 0, so if all possible values of this random variable are greater than or equal to 0, then the expected value of x must also be greater than or equal to 0. Should be self-explanatory. You can't somehow magically get a negative number in an expected value if you don't have any possible outcomes that are negative. And then the second rule is pretty much the same, and it's just really a more generalized form, and we're not going to dig into the proof of this, but basically saying that there is a lower limit a and an upper limit b to the random variable x. So all possible outputs of the random variable x fall between a and b. And if that's the case, then the expected value of x also has to fall between a and b. There is no way to get an expected value outside of that range as long as you limit all values of your random variable to that range. Then the last one we'll look at is that if we have some constant c that is a input to a expected value formula. So if c is a constant, then the expected value of c is just c. Again, should make sense. There's only one possible outcome because c is a constant. So if we look at the probability mass function there, you're going to have a value of c with a probability of 1. And so the expected value is always just going to be that value c.